In this graph, we will look at continuity and come up with ways to determine when a function is continuous. In particular, if it's a function that is not as easy to see close up in particular points in a graphing software like Desmos. In this first slide, we're looking at a practical application in which we may have collected particular data points and plot them on a graph. And then to model the data and maybe predict what's happening, let's say out in some future point in time, we would connect these points with a smooth curve. And by doing so, hold on a second, here we go. By doing so, we're making the assumption that, say, a y value may be here or a y value here, any y value that's in between some of the given points, that the function takes on those values. When we assume that all the y values are taken on, that's saying that we're assuming that the function is continuous. In this slide, we have a picture of a graph that we used in a homework example, I think last week, where we've got a number of places that we can see that the function is not continuous. Specifically at x equals 1, at x equals 2, and at x equals 4. For number 1, we call this a jump discontinuity because we can see that there is a jump in where the y values are for the function. In x equals 2 and 4, those are removable discontinuities because the function is defined in a different location than where the graph is approaching, if we were to think about it in terms of limits. The second part of this slide, like this part down here, is talking about what the different limits are as we look at the various values. For example, if I look at x equals 2, I can say that the limit exists because both the left hand and the right hand limit are approaching the same number. But at x equals 1, the limit does not exist because the left hand and the right hand limits are not the same. Here's the left hand one, and here's the right hand one. When we look at x equals 4 over here, we can say that the limit overall doesn't exist because only the left hand limit is defined. And the right hand limit is not, the function's not even defined over to the right of x equals 4. But the interesting thing is that we will say in certain contexts that something is maybe left continuous, that it's continuous leading up to a point, or right continuous, just because it's leading up to a particular point. We'll see, I think, in the next slide or so. For example, right here at x equals 0, this is right continuous because the graph does touch all of the y values as it approaches the limit of as x approaches 0. So here are the formal definitions of continuity. We'll say that a function is in fact continuous at a particular point, c in this case, if the limit exists and when we plug that value c in for x, we actually get the y value, right? That the output matches what the limit is. Similarly, we can talk about just a right-handed limit, which would be this example down here, where we say, okay, similarly, the function value is defined right at the point in question, at the x value we're looking at, even though the graph doesn't extend beyond that point. And then also we've got the left-hand limit looking at the other direction. Going back to the graph that we had before, the function is not continuous at x equals 1, right here, because the limit does not exist, right? We said that before. Left and right hand limits are not the same. At x equals 1, though, the function is right continuous because the limit that we're approaching from the right is equal to the value of the point at x equals 1. So because we have a closed circle, we can say that the right-hand limit exists. and it's right continuous, continuous from the right. At x equals 2, the function is not continuous because the function is not defined to be what the limit is, approaching from both sides. So these are not continuous for different reasons. And then at x equals 4, the left-hand limit exists as we approach from the left, but the function value is not defined to be exactly the same at that point, so we can't say that it is left continuous. So again, we're putting this combination of things together of the limit that something is approaching and whether it actually takes on, the function takes on that value that the limit is approaching. Sort of obvious, but worth stating that at other points on the graph, like let's say 1.5 over here, or at x equals 3, or even x equals 0, the function is continuous, though at x equals 0, we would say that it's continuous from the right. In this function, we can see that the function is continuous from -2 to 2 and everywhere in between. But it is right continuous at, so when I look at the domain, I'm looking at just these numbers in between -2 and 2, but I can also say that it's right continuous as I look at, say, this point here, because from the right we have this right-hand limit approaching the value. And then over here we would say that it's left continuous because we have the limit approaching the output value there. This is a step function where the function takes on two different values, one in the negative x values and then, or 0 in the negative x values and 1 in the positive x values. There's a jump discontinuity here because we can see that there's this space in the middle between the two parts of the graph. But we can say that it is right continuous at x equals 0, again, because the limit that the function is approaching matches up with what the function value is at that point, x equals 0. So this is the test that we'll use to determine whether something is continuous. We first have to see that the point that we're trying to test for continuity is within the domain of the function. Obviously, we can't plug in a point that's maybe going to make the denominator equal 0 or have us taking the square root of a negative number. The limit has to exist as we approach the point in question. And the third, which is the most important, is that not only does the limit exist, but that the limit matches up with the function value. Here are a couple of examples. Probably overkill at this point, but letter A is obviously continuous. The rest are not because there are holes in the graph, or in this case, we've got, like in the graph E, we've got an asymptote here, and both sides of the graph are shooting up to positive infinity, but even though they both have the same limit from the left and the right, at x equals 0, the graph isn't going to take on any value. And then similarly here, neither of these graphs are defined when x equals 0, so we can't say that it's continuous at x equals 0. These properties are probably pretty easy to understand. If we have two functions that are both continuous, we can add them together to get another continuous function, or we could subtract them to get another continuous function, and so forth. So combining the two functions algebraically will result in another continuous function. This theorem, though, is a little bit more complex because now we're talking about composition functions. As a reminder, that's when we take one function and we plug it into the other function in place of the variable. And so in this example, we can see that the two functions that we started with, x times the sine of x, that on its own is a continuous function. And then the other function is x squared plus 2. That on its own is a continuous function. So when we combine them together in this ratio, we're still going to end up with something, even though it's a really cool graph and looks really interesting, it is continuous, which is the point that we want to make. So here more formally is the proof. This is a delta epsilon proof. We have to show that for any epsilon that's greater than 0, we can find, well, this is actually starting with the proof is starting with the definition. For any epsilon greater than 0, because g is already continuous at b, we know that there's a delta greater than 0, such that when the function values are within the neighborhood of epsilon, then the input values are going to be within this delta neighborhood. So that's drawing on the definition of limit that we talked about in the last class. And then what we're saying is that all we're really doing is we're taking this idea that y equals f of x, and we're making a variable exchange, right? Here we've got f of x, but we're going to switch it to be y. And then when we're plugging those into the function, here, this is going to extend to this. Again, this is here if you want to take a look at it, but don't need to worry about this too much. Just showing you that, in fact, a delta epsilon proof will show that this is true. So let's use this idea of continuous functions. Again, the main thing that's important to take away from this is that I have two different functions and they are separate from one another. And so I can separate them in a way that helps me analyze what's happening. As is the case in this example, I have cosine is its own function, and then I've got this other function on the inside, right? 2x plus the sine of something. Notice that what we're going to do is take the limit and we're going to move it inside the parentheses, and then cosine is going to come out to the front. Again, the composition function is cosine of something. So all we're doing is exchanging the order of where cosine and where limit are, so that we can take the limit of 2x on its own. Well, that's pretty easy, right? If I put pi over 2 in there, I'm going to get pi. That's right here. And then I can, for this other part, sine of 3 pi over 2, I can plug pi over 2 in for x, and I'm going to be taking the sine of 2x. So again, the theorem is really just saying that because we can move where the limit and that cosine function are, it allows us to take the pi over 2 and plug it in for the variables. The second example is a similar type of example where you can see that in this stage right here, we're swapping where the sine of x and where the limit are. And so that allows us to think about what the limit of this rational function is without worrying about the sine inverse function. To analyze this rational function, we factored so that we could cancel a factor, and then we're able to plug 1 in. And then we can see that we're just trying to find sine inverse of 1/2, which is pi over 6. The intermediate value theorem is one that also seems sort of obvious, but it's one that we use a lot when we're trying to find zeros, or we used to use it a lot before the invention of Desmos and things like that, where we can zoom in on a graph pretty well a lot of the time. But before we were allowed to have graphing calculators in class, or they weren't readily available, we would use this idea that if I know, let's say that this is the y-axis. If I know that one of the function values, let's say here, is below the x-axis, and I know that one of the function values here is above the x-axis, then somewhere in between these two, the graph has to pass through 0. It has to pass through the y-axis at some point. Oh, hi, why am I saying y-axis? That's x-axis. Bad teacher. That the graph has to pass through the x-axis, or y equals 0. That's why I was thinking y equals 0. That doesn't have to be the x-axis, though. It could be any value. I could say, all right, let's say that this line is at y equals 3. If I have a value here that's below, let's say this is 2 and up here is 7, I know that the function at some point, if it's continuous, has to pass through the value y equals 3. Again, we typically use this when we're trying to find zeros of a function. Let's look at the second example first. In the second example, we have the function x cubed minus x minus 1. This graph over here doesn't look like the function at all. It's just a picture of a zoomed in really, really close to see where that 0 is. We're asked to show that there's a root or a 0 of the function between x equals 1 and x equals 2. So if I plug 1 into the function, I see that I get -1 as the output. That's less than 0, so somewhere down here. And then if I plug 2 into the function, I get 5, which is above 0, so somewhere up here. So I know that somewhere between 1 and 2, I've got to have this location that the function passes through and it takes on the value of 0. By zooming in really tightly to the function, maybe in, like I said, in Desmos or something, we could estimate that the x value occurs at maybe approximately 1.3. Going back up to this first graph, we can see that this is a piecewise function. It takes on all the values between when x is equal to 1 and when x is equal to 2. It takes on all the function values in between those two, right? Between 0 and 2 in that case. And it doesn't take on any of the values here. Wait, between 2 and 3? Oh, this means the y values. This is talking about the y values, right? Kind of obvious because it's a simple graph. All right, so let's use the intermediate value theorem to show that this function, which is somewhat complicated, but it's really just two functions put together, has a solution. The way we would graph this in Desmos, we've got two separate graphs. Notice that the graph of the first one cuts off because the domain is restricted, because we can't take the square root of a negative number. And then we've got, oh, this is the square root graph, sorry, right here. And because that domain's restricted, we have to restrict the domain of the parabola. The first thing that we do, you'll notice here, is that we put everything onto one side and 0 onto the other so that we can look at this as a single function. I'm going to have the first part be the function f, so this part is going to be the function f, and this part's going to be the function g. So when I combine them together, adding them, I've got two continuous functions, and so I'm adding them together, and I know that they will still be continuous. Notice that the domain is this. We get that by setting up that 2x plus 5 has to be greater than or equal to 0, and just solve, right, to figure out what the domain is for that square root function. Now, back in the old days when I was taking math, we would have to just use trial and error to plug in values to kind of figure out where the 0 might be in between. But obviously now we can use Desmos and we can kind of look at the graph and see. If we looked at the graph in Desmos, we'd see, okay, if I plug 0 and I'm getting this negative number, if I plug 2 and I'm getting this negative number, so there has to be a 0 somewhere between 0 and 2. And so then we just conclude that there is some number, c, we don't know what it is, that's in this interval such that the original function, this guy, does take on the y value of 0. And then this is the last slide, which is just a handy bit of information, which is called continuous extension of a point. In this first graph, I can see that I have 2 is removed from the domain, because if I plug 2 and I'm going to get 0 in the denominator. So what we can do to get continuity of the function is we just redefine the function. We just say, well, we know that the function isn't defined when x equals 2, but if I just say, okay, well, the value that the limit is approaching is 5/4, I'll just add that in and make it a piecewise function and just add that little point in that was missing, so then the function's continuous. Similarly, for this graph on the right, we know that sine of x over x is undefined when x is equal to 0. This is a little hard to read. This is the sine of x over x. So we have this whole at 0. But if we just set up a secondary definition to say, okay, well, when x is equal to 0, we'll let the function take on the value 1, then we now have continuity there because we just basically color in the hole with the point that we want to make it continuous. All right, thank you for watching, and I will see you in class.